We thought reaching Pluto was the achievement of the century. 9 years of travel, 3 billion miles, a spacecraft hitting a target the size of a continent after almost a decade in transit, with millimeter-level precision. The total mission cost nearly $700 million. The team that designed it, hundreds of scientists across multiple countries. The launch window a few weeks, after which the geometry would close and the entire trajectory would have to be recalculated for years later. And yet, on a cosmic scale, Pluto is in our backyard. If reaching Pluto is a walk through the neighborhood, reaching Proxima Centauri is a mountain we still do not know how to climb. Because with the technology that took us to the edge of the solar system, we would all die long before seeing the light of another star. Not because of bad luck, not because we are not trying, because the physics of space travel does not care about human ambition. This is the brutal physics that makes interstellar travel almost impossible. And by the end of this episode, you will understand why no spacecraft we have ever built, are currently building, or have seriously planned can do what every science fiction movie pretends is just a matter of pressing a button. Start with what New Horizons actually was. A spacecraft about the size and weight of a grand piano. Roughly 1,000 pounds it launched, powered by a single radioisotope thermoelectric generator producing about 200 watts of electricity. That is less power than 2 old-fashioned light bulbs. And that was enough, because New Horizons did not need to eat. It did not need to breathe. It did not need shielding from radiation strong enough to keep a human nervous system functional for years on end. It did not need to be entertained or kept sane, or kept warm in any meaningful biological sense. It needed power for its instruments, fuel for its small attitude thrusters, and a working radio. Total mass, less than half a ton. That is the kind of payload chemical rockets can launch. Now consider what would actually be required to send humans to Proxima Centauri. The journey, even at the most optimistic propulsion speeds being seriously researched today, would take decades, possibly more than 100 years. A crew traveling that long cannot be sent in a tin can. They need food, water, breathable air, replacement parts, medicine, and a closed-loop life support system that does not fail across multiple generations. They need protection against radiation. They need exercise equipment to prevent muscle atrophy. They need crops, soil, recyclers. They need backups for every critical system. And they need backups for the backups. This is the concept of a generation ship, a vessel designed not to deliver a single human crew to another star, but to support an entire small civilization across multiple generations. The people who arrive at Proxima Centauri are not the same people who left Earth. They are the descendants of those people 2 or 3 generations removed. Recent engineering studies suggest a viable generation ship would need a minimum population of around 500 people to maintain genetic diversity, and a total mass of several million tons. For comparison, the International Space Station weighs about 460 tons. A generation ship would need to be 10,000 times larger, and the math turns hostile fast. The bigger the ship, the more fuel you need to push it. The more fuel you carry, the heavier the ship becomes. The heavier the ship becomes, the more fuel you need to push it. This is the tyranny of the rocket equation, and it does not behave linearly. It behaves exponentially. Doubling your target speed does not double your fuel requirement. It can multiply it by a factor of 10 or 100, depending on your engine. To put this in perspective, to reach even 1% of the speed of light using conventional chemical rockets, you would need roughly 10 to the power of 26 kilograms of fuel for every kilogram of spacecraft. That is more mass than the entire planet Earth. Not a practical solution, not even close. To Pluto, you send a computer. To Proxima Centauri, you have to send a civilization. And the moment you scale the spacecraft up to that size, the mission becomes a mathematical paradox that no chemical rocket and no nuclear engine known today can resolve. This is why interstellar travel is not just a longer version of going to Pluto. It is a categorically different problem. The same physics that allowed us to send a piano-sized robot past a distant dwarf planet actively works against us when we try to scale that mission up to interstellar distances. Every variable that helped New Horizons succeed becomes an obstacle for Proxima Centauri. The space between Pluto and Proxima Centauri is not a calm void. It is a hostile environment that we have only barely begun to study, because we have only barely sent anything into it. Inside the solar system, even out at Pluto's distance, our spacecraft are still partly protected by the heliosphere. This is the bubble of charged particles flowing outward from the Sun, which deflects most of the high-energy cosmic radiation coming from outside. The heliosphere is not perfect protection, but it cuts the cosmic ray flux roughly in half compared to true interstellar space. The boundary of that bubble is called the heliopause. Voyager 1 crossed it in August 2012 at a distance of about 11 billion miles from the Sun. Voyager 2 crossed it 6 years later. They are the only two human-made objects ever to operate in true interstellar space. And once you are past that boundary, the rules change. Cosmic rays in interstellar space are dominated by high-energy protons and atomic nuclei, accelerated by supernovae across the galaxy. They travel at relativistic speeds. They penetrate spacecraft hulls. They damage electronics through single-event upsets. They mutate DNA in any biological material they pass through. For a human crew on a multi-decade interstellar mission, the cumulative radiation exposure would be lethal without shielding measured in meters of water or hydrogen-rich material, adding more mass to a spacecraft that is already too massive to launch. Then there is the dust problem. Interstellar space contains microscopic grains of dust at extremely low densities. And at Pluto's distance, this is not a meaningful concern, but once you are traveling at significant fractions of the speed of light, even a single grain of dust hits the spacecraft with the energy of a small explosion. A spacecraft moving at 20% of the speed of light hits an interstellar dust grain with energy comparable to a high-velocity rifle round. Now, factor in time. New Horizons was engineered to operate for roughly 15 to 20 years. That is already an extraordinary engineering achievement. Every component on board has to be radiation hardened, redundantly built and tested for decades of uninterrupted function in the cold and dark. A mission to Proxima Centauri at 1% of the speed of light would take about 425 years. A mission at conventional Voyager speeds would take about 76,000 years. There is no material on Earth that does not degrade across that timescale. Plastics break down, metals fatigue and crack. Electronic components suffer from cumulative radiation damage. Lubricants evaporate. Solid-state memory loses its stored data. Even if every other problem were solved, the spacecraft would arrive as a non-functioning artifact. Building hardware that can survive a 70,000-year journey in deep space is not currently solvable. We do not even know what such a material would be made of. Glass turns cloudy on those timescales. Steel rusts even with traces of moisture and oxygen. Polymers crystallize and crack. Even the gold-plated record carried by the Voyager probes is only expected to remain readable for about 1 billion years in deep space. And that is because nothing on the spacecraft is moving or being stressed during the journey. Add moving parts, computers, life support, and the lifetime drops by orders of magnitude. And the cosmic ray problem becomes worse over time, not better. Every single charged particle that hits a circuit board has a chance of flipping a bit, corrupting memory, or destroying a transistor outright. On a 15-year mission like New Horizons, you can statistically tolerate this with redundant systems. On a 70,000-year mission, every single circuit will be hit catastrophically thousands of times. There is no redundancy that survives that. Everything we've just described, the rocket equation, the radiation environment, the materials problem, only gets worse when you try to slow down. And the deceleration problem is the one almost nobody ever talks about. Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos and you'll miss what we uncover next. When New Horizons reached Pluto, it did something that the public rarely understands. It did not stop. It could not stop. The probe screamed past Pluto at 31,000 miles per hour, capturing every photograph and measurement it could during a few short hours of close approach, and then continued outward into the Kuiper Belt. There was no entering orbit, there was no landing, there was no second chance. And the reason for that is the same reason interstellar travel is so much harder than the public typically realizes. In space, there is no friction. Once a spacecraft reaches its cruising speed, it stays at that speed forever with the engines off. This is useful for long journeys because you only burn fuel at the beginning of the trip. But it also means that bringing the spacecraft back down to a manageable speed at the end requires exactly as much energy as it took to get the spacecraft moving in the first place. If you want to fly past Proxima Centauri, you only need to solve the acceleration problem. If you want to actually live there, you have to solve both. And the math here is genuinely cruel. Under the rocket equation, requiring the spacecraft to brake on arrival does not double the fuel requirement. It squares it. A vessel with enough fuel to reach 10% of the speed of light and then decelerate to a stop on arrival needs vastly more starting mass than a vessel that just flies past at full speed. Let's put this in concrete numbers. The fastest spacecraft ever launched was the Parker Solar Probe, which during its closest approaches to the Sun reached speeds of about 430,000 miles per hour. That sounds extraordinary. It is extraordinary. And yet, even at that velocity, traveling in a straight line toward Proxima Centauri, the journey would still take more than 6,500 years. And Parker only achieves that speed because it falls toward the Sun under gravity. It cannot maintain that velocity going outward because nothing is pulling it. For a spacecraft massing several million tons, traveling at relativistic speeds, the energy required to decelerate is comparable to the total energy output of a major nation's electrical grid running for years. Nuclear reactors, you would need thousands of them. Solar panels, at Proxima's distance, sunlight from our sun is essentially zero, and the destination star puts out only a fraction of what our sun does. Chemical fuel, you would need a fuel tank larger than the spacecraft itself, recursively, until the entire concept collapses under the rocket equation. Where do you carry that fuel? There are some clever proposals on the table. The most studied involves using the destination star's own light as a brake. As the spacecraft approaches Proxima Centauri, the light from that star hits a large reflective sail from the front, providing gentle deceleration without any onboard fuel. This is the same physics as breakthrough starshot, but running in reverse. In theory, it could work. In practice, it has never been demonstrated, and the engineering tolerances required are extreme. The sail must deploy at exactly the right moment, at exactly the right angle, with no error correction possible from Earth because the round-trip signal time is over 8 years. Other proposals invoke antimatter engines, where the annihilation of matter and antimatter releases energy at maximum theoretical efficiency. A single gram of antimatter could in principle provide the energy of a small nuclear weapon, but humanity has produced only nanograms of antimatter in total, and energy costs trillions of times higher than the energy you would get from using it. Antimatter propulsion is the only known concept that could decelerate a large interstellar mission within reasonable mass constraints. It is also, for the foreseeable future, pure science fiction. The current estimated cost to produce 1 gram of antimatter is somewhere around $62 trillion. That is more than 3 times the annual GDP of the United States. For 1 gram, a meaningful interstellar mission would require kilograms. Until that situation changes, every serious interstellar concept has the same problem. You can leave Earth, you cannot arrive. Pluto taught us how to walk through our own neighborhood. It taught us about the rocket equation, gravity assists, the cold of deep space, the difficulty of communicating across vast distances, and the relentless trade-offs between mass, fuel, and speed. It taught us that even reaching the edge of our own solar system requires 50 years of engineering preparation, the assistance of a giant planet's gravity, and a spacecraft that can only afford to fly past its target for a few hours before continuing onward forever. But to run toward the stars, we have to reinvent the physics of propulsion entirely. Conventional chemical rockets, ion engines, and the most advanced plasma drives currently flying are all incapable of producing the kind of speed required. Even nuclear pulse propulsion, the most studied serious concept for genuine interstellar speeds, would only barely work, and it requires detonating thousands of nuclear weapons in space across decades of acceleration. The propulsion methods that could actually solve the problem like antimatter engines, fusion drives operating at theoretical maximum efficiency, or laser sails delivering hundreds of gigawatts of focused power across multiple light years, are either centuries away from being engineered or fundamentally incompatible with crewed missions, or both. And yet the conversation is no longer purely theoretical. There are funded research programs working on the early stages of these technologies. There are physicists, engineers, and aerospace teams who treat the question of interstellar travel not as a fantasy, but as a long-term engineering project. The Breakthrough Starshot Initiative has committed $100 million to studying gram-scale laser-propelled probes. NASA's Initiative Advanced Concepts program funds research into fusion propulsion, antimatter catalysis, and exotic propulsion theory every year. The work is being done. It is just being done with the honest understanding that the timeline is not measured in decades, it is measured in generations. Pluto is the destination that taught us how hard space really is. Proxima Centauri is the destination that will teach us whether we can actually become an interstellar civilization, or whether we are permanently confined to one star system. We do not have the answer yet. What would you sacrifice for a one-way trip toward another sun? Tell us in the comments. There is one spacecraft already on its way out of the solar system, the fastest object humanity has ever launched. And people often ask the same question: could it ever reach another star? Watch Will Voyager reach Alpha Centauri next. The answer is more interesting than you'd expect.